surface crystallography, just like our crystal crystallography that we studied a couple of lectures. Okay, so and they are a little bit simpler, as we'll see. A surface is a two-dimensional object, right? And in theory, they are imaginary plane. But by surface structure, what we are talking about is actually this. Again, I present you with this self-edge idea. They are actually have finite space. You know, the word surface really just means this virtual object that's just a two-dimensional virtual plane that you have. But in our mind, we should think when we talk about surface, actually has some volume, because the volume is created by a couple, two or three planes, perhaps, the so-called self-edge region, right? Because these are the region where the first plane and the second plane, these spacing are changing slightly until we hit the bulk, what we consider bulk, whereby the d spacing no longer change. So the top layer, this self-edge region, is what we often think of as the surface, instead of just the first plane that we have. Okay, so that's a very good picture that we should, whenever we think about surface, we should think about there is actually some skin. You can think of it as a skin, because skin has thickness too. That's our surface, like this. So we would generally mean that in the vicinity of the surface, so it's not just this plane, but the whole bit that we have. Or the region of two-dimensional vicinity whereby no plasticity in the dimension in the depth direction, in the bulk direction that we see. Okay, and first of all, in order to start talking about this crystallography, I want to just first look at clean surface, nice clean surface, like our ideal concept of clean surface, that we don't allow the atom to move about. No reconstruction, no relaxation. The atom stay put after I cut the bulk to create my surface. And I put in notes here as a cautionary note that what happens is that in most cases, when you cut the surface, of course, in real world, what happens is that the surface will reconstruct, right? Once the surface becomes free, so when you cut the surface, become free of absorbate, no absorbate on top either, just good old plain surfaces. These surface atoms will reconstruct, right? Both in the XY direction and of course in the Z direction as well. In order, why do you reconstruct? You can construct in order to obtain a lower total energy, and this includes all silicon or germanium, gallium arsenide, gold, platinum, all these surfaces. You have lateral reconstruction in real life, but we are not talking about this yet. And this reconstruction, of course, changed the original structure, but then what even more interesting? So you have clean surface, they will reconstruct, but sometimes you also have reconstruction or surface structure. You put absorbate on top. Let's say you expose CO on top of platinum, right? And actually, the CO itself would go for the individual site, regular site on this atom. And sometimes it may relax, de-reconstruct the surface itself. So if you have clean surface, the surface element move about, but then once you put some absorbate on top, it reverted back to a structure very close to the bulk for the first layer. So there are many sort of different things could occur, interesting things that could occur when you put absorbate on top of a clean surface. Okay, so very quickly now, so that's a preliminary thing. Very quickly, we'd like to talk a little bit about symmetry operation. Just like before, my discussion very parallel to the bulk discussion. We have 7 symmetry operations. We have no operation, just one fold rotation, rotate by 380 degree or identity operation. You always have identity operation. And then you have 4 different rotations, 2-fold, 3-fold, 4-fold, 6-fold. Notice no 5-fold or 7-fold, things like that. So no 5-fold because there's nature does not like 5-fold symmetry at all. And you only have these 4 different type of rotation. There's mirror refraction, of course, your plane just reflect, and there's something called glide refraction, you reflect and then move half the spacing. So here's what we discussed here. So this is identity, and then you have rotation by 2, rotation by 3-fold, 4-fold, and 6-fold. And then in here you have added mirror refraction to this row here to generate these other thing. And then this is just mirror refraction. And this is a glide refraction, so you reflect and then move half the lattice spacing. Okay? So next day I'm going to continue to give you a quick introduction of these things, and then I'll talk, hopefully we can talk a little bit about the electron diffraction when we get to it. I have put out a assignment on the web, so people should download the assignment. And you have a little write-up for me. So you can either email it to me or give it to me sometime this week before the next lecture. Okay, this is about the abstract on your term paper. Okay, so I want to general outline, and I have received your abstract, Jeff. On the other side, I got your